Good afternoon, everybody. This is MD Masumbilla, student ID 19ME117, presenting my research titled Headcut Migration in Earthen Embankment Induced by Varying Subsurface and Seepage State during Overtopping Flow, supervised by Associate Professor Junji Yagisawa. Today, I will be explaining my research to you by this flowing content, starting from introduction, then methodology, equipments and techniques, results and discussion, conclusion, and finally, limitation and recommendations. As we know, earthen embankment is considered to be the most economic and effective means to withstand against natural disaster. And this earthen embankment is designed for a certain design level. But due to extreme event like flood or tsunami, this embankment overtops. And it is found that 40 to 48% reported case of embankment failure is due to overtopping. And as the overtopping is not considered in the design of earthen embankment, so when overtopping takes place, complete breaching is expected. During an overtopping flow event, at the downstream to the embankment, large flow shear stress develops. This causes a scour at the toe, having a steep face, called head cut, starts to migrate with time until complete breaching of the embankment takes place. This photo shows the 4 stages of cohesive embankment breaching process. First, overflow starts, and then with time, at the downstream, head cut forms and flow is concentrated. And once the head cut forms, it starts to migrate with the time until complete breaching takes place. So from this photo, we can see the total time required to form a breach is dependent on head cut formation and its migration. And that time is very important for flood evacuation planning. That is why head cut migration is a key interest to the hydraulic researcher. Previously, many geotechnical and hydraulic factors that affect head cut have been studied by several researchers. But still, complete understanding of head cut erosion phenomena is far from mature. In our study, 2 important phenomena during and after construction of the embankment is under consideration. Firstly, hard subsurface. Usually, the soft soil from the top is removed during the construction of the embankment to get a hard surface to perform well against earthquake, under seepage, and settlement. Secondly, prolonged immersion takes place during a flood event, which causes the decrease in shear strength and affects the failure mechanism of embankment. So based on these 2 phenomena and previous research limitation, we set our research objective as how the erosion resistant layer under the embankment and prolonged immersion affect the head cut migration during a overtopping flow is our main objective. To achieve our objective, initially we constructed 4 embankment model, having 3 different positions of erosion resistant layer as 1.5, 3 and 4.5 centimeter, and 1 case without any erosion resistant layer. To check the effect of prolonged immersion, we constructed another 8 embankment model. First for H/6 permeation, that means fixed headwater causes the phreatic line to intercept the downstream slope at H/6. On the other hand, another 4 embankments were conducted under H/3 permeation. That means the phreatic line intercept the downstream slope at H/3. Then all the 12 embankment model were conducted under fixed overtopping depth flow 3.5 centimeter. To fix the erosion resistant layer position under the embankment, initially we conducted experiment without any erosion resistant layer, and the scour depth was measured and found to be maximum 5.5 centimeter. So based on this maximum scour depth, we selected 3 different positions of erosion resistant layer as 1.5, 3 and 4.5 centimeter. To construct our embankment model, we used lime improved soil having D50 0.66 millimeter, and as the soil compaction degree, dry density and moisture content have significant effect on head cut migration. So throughout all cases, we control these properties so that it does not affect the head cut migration. The embankment model in the laboratory were constructed layer by layer with a manual compactor having lip thickness 5 centimeters. This is the final embankment model. And to confirm the phreatic line position, we looked at the channel sidewall and easily distinguished the unsaturated and saturated zone. Here, the red dashed line indicates the phreatic line. Also, we noticed some water at the downstream toe of the embankment to confirm the phreatic line position. Now, to catch the eroded profile of the embankment without stopping overtopping flow, we inserted RF tags systematically into the embankment, layer by layer, throughout the downstream slope region as shown in this figure. The each layer-to-layer distance were kept 5 centimeter, and in a certain layer, the tracer-to-tracer distance were also kept 5 centimeter. Then the embankment was prepared to be overtopped. Before start of the overtopping flow, the RF tag reader were connected with a computer so that it can detect this RF tag continuously. And when the overtopping flow starts, a scour at the toe takes place and tracer inside the embankment body comes out and starts to flow with the water. And at the downstream, we continuously detected this tracer throughout the experiment period, as shown here. This red dot shows tracer detected. So based on this, and this photo shows the tracer ID and corresponding detection time. So based on this detection time and previously known position data, we generated 3D contour map throughout the experiment of the embankment profile. To get the headcut position in the 3D contour map, we followed the criteria where the eroded face exceeded 60 degree or free nap form. We refer to that position as headcut position. For the case 3.3, here the headcut position is shown by the black dots that starts to migrate with the time. Now the dimensional headcut position obtained from the distance of headcut normalized with the horizontal sloping distance or plotted with this elapsed time shows that with the decrease in depth to the erosion resistant layer, headcut migration speed increases by 1.86 times higher. This is for 1.5, 3, 4.5 and no erosion resistant layer. Initially, we observed faster erosion rate, and in the second stage, we observed slower speed. The faster speed is due to the mass wasting phenomena, and the second stage are due to the progressive surface erosion phenomena. Here, schematically, the mass wasting phenomena shown. Hydraulic jump takes place, and then soil collapses down. And in the second stage, free nap forms, and this nap is deflected by the surface erosion, and then progressive surface erosion takes place. And this process continues to repeat. For the case of erosion resistant layer at 4.5 and no erosion resistant layer, we observe the similar rate throughout the experiment, governed by only progressive surface erosion. As mentioned earlier, the mass wasting phenomena responsible by cleansing nap and hydraulic jump causes undercutting, and that leads to the mass wasting. And just after mass wasting, free nap forms and immediately converts into the cleansing nap. And the second stage, free naps forms, which impedes the large pool and stops the mass wasting, thus the speed gets reduced. The shallower erodible layer causes faster erosion because the scour created is shallow and the tail water is low and headcut face remains steep, causes the low energy distribution. On the other hand, for the deeper erodible layer case, large pool created and high tail water forms, which causes more energy to dissipate and responsible for slower headcut progress. When prolonged immersion were incorporated, it was noticed that for the erosion resistant layer at 1.5 and 3, similar pattern observed. Initially, the speed was governed by the both seepage and erosion resistant layer. Later, we easily distinguish the seepage condition. Here, H/3 had seepage, mid seepage, H/6, and no seepage. Same happened in the case of 3 centimeter ear layer condition. So we easily confirm the dominance of seepage for the shallower ear layer position. For erosion resistant layer at 4.5 and no erosion resistant layer, we observed similar pattern. Throughout the experiment, the X-hat and the elapsed time plot shows that continuously the seepage governs. This happens because as the erosion resistant layer approaches to the maximum depth 5.5, so effect of erosion resistant layer becomes submissive. And it was 2.03 times higher for no erosion resistant case and 2.3 times higher than the no permission cases. Seepage dominance also confirmed from the plot of lower seepage cases and higher seepage cases. The lower seepage case, that means the H/6 permeation cases, shows that still the effect of erosion resistant layer is visible, indicating the wide range. On the other hand, for higher seepage cases, we notice that irrespective of erosion resistant layer position, the speed remains same. So with the increase of intensity of seepage, the dominance of our erosion resistant layer also increased. So from our experiment, we concluded that the erosion resistant layer under the embankment has significant effect on the headcut migration toward upstream. And with the decrease in depth to erosion resistant layer, headcut migration speed get faster and vice versa. And decrease in depth to erosion resistant layer from 4.5 to 1.5, the headcut migration speed increased by 1.2 to 1.86 times higher than the case of no erosion resistant layer. For shallower depth to erosion resistant layer, initially, the headcut migration speed is governed by the mass stream phenomena, and the slower speed is caused by the progressive surfacation phenomena. When the prolonged immersion are incorporated, we notice that initially the speed is contributed by both erosion resistant layer position and seepage adjusted, but later seepage starts to dominate the migration rate. So in our study, we have some limitation. We replicated the real embankment into the model, but we couldn't apply any scale factors. So practically, erosion phenomena may be changed. And the tracer to tracer center distance were kept 5 centimeters. So measurement accuracy got reduced. So we recommend to conduct the large scale model and apply the existing headcut model to our result to modify so that we can predict the real embankment breaching phenomena in the practical site condition. That is all. Thank you very much for listening.
Thank you for your presentation. So I'd like to move on to the question and answer session. So if you have a question or a comment, please let us know. Yes, Tanaka-sensei, please.
Yeah. If erosion resistant layer is located on the surface or shallower depths, hydraulic jump itself is not easy to be occurred near the levee toe. Okay, in that case, how ER layer affects the erosion process? It increases, increases or decreases the erosion? How it affects, do you think?
If we plot the hard layer on the surface, I feel that depending on tail water depth, the headcut migration will be affected. If the tail water, maybe in that case, I feel tail water depth will be reduced, so migration speed maybe will be faster.
Mm-hmm. It depends on the tailwater depth, ne?
Yes. So
okay.
More tailwater depth causes more energy dissipation. So in case of zero, the foundation level is in position, so I feel migration speed will be faster.
Okay, yeah.
Thank you, sir.
Yeah.
Thank you, Tanaka-sensei. Next, if you have any questions, please let us know. Yes, To-sensei, please.
Sure. As you show you the devices, all the figures is almost in the 2-dimensional. So I'm wondering, how about the water flows from the, if they need a lot of receiver to cover one part of the river bank? Do you have this kind of information?
This is just overtopping phenomena. So headcut forms actually certain part of the embankment. So embankment is a long structure, but headcut forms at a certain position. So we consider the small width like this throughout the channel.
Yeah, this is in your experiment, but in the real river, there will be very long river, right? So one receiver will only cover, let's say, 5 meters or more. So you maybe need a lot of receivers, right? So how do you think to one receiver to cover how long area you need? Or you already know where it's definitely going to be overflow by your some other information? That's my question.
Thanks.
Or your strategy just to cover using a lot of receivers to cover a lot of areas.
Sorry, Sensei?
Or your strategy is just using a lot of receiver to cover all the areas you're going to cover. Or you point some place.
Yes, Sensei, it is just a coincidence. If in some site, there is a erosion resistant layer present, and at that place, overtopping takes place. So that comply with my experiment. But maybe it is not practical that throughout the embankment length, there will be erosion resistant layer under the embankment.
Oh, I see. So another question. I think you need to put this signal sender inside the bank. So is that expensive to put them into there? You need to reconstruction the bank area or something?
It is just actually I have mentioned that overtopping is not considered in the design of the embankment. So from this experiment, we know how the erosion takes place, and then we can predict the breaching so that we can plan for the flood evacuation planning. But I couldn't focus on the preventive measures. I tried to understand the phenomena.
Okay, this is just a proof of concept. I see, understand. Thank you very much.
Thank you, sir.
Thank you, Sensei. Any further question? We have still 2 more minutes. Okay, if there is no question, I'll ask one question. In your experimental work, you didn't consider the effect of any vegetation, but in reality, in the real river, for example, you see the vegetation is always there. So how the vegetation, presence or absence of vegetation will change the result?
You mean the vegetation at the slope, grass?
Yeah, slope at the graph or at the downstream, for example.
So I feel that if there is grass on the slope, so stability of embankment will be more. That means the erodibility of the embankment got reduced. And in case the vegetation is on the far from the embankment, so it will block the water, and then the tailwater depth also will be increased. So migration speed, I feel reduce.
Okay, but you haven't confirmed yet, right?
Yes.
In your experiment, you didn't consider.
Yes.
Okay, I understand. Okay, so there is still time for a very quick question. Like we have a couple of seconds remaining, like 30 seconds around. If you have any questions, please let us know. Okay, if there is no any further question, I'd like to move on to the next presenter. Thank you very much for your presentation.
Thank you.
So